Thank you so much for the introduction. I'm Robert, and I'll be talking about a joint work with Sitan Chen and John Praskol on learning to predict arbitrary quantum processes. So, as we have seen from the past few years, there have been a lot of progress on how to efficiently learn and how to efficiently predict properties about quantum states. However, less is known about learning to predict quantum circuits and processes, which can be important for understanding many important applications, such as how different molecules are interacting with one another, or dynamics that happens in exotic quantum matter, in quantum devices, etc. So for today's talk, I would like to essentially make progress and try to fill in this gap on how to design efficient algorithms for learning to predict quantum processes. In particular, in today's talk, I'll be focusing on training an ML model to learn and predict a function that look like the following. So we're given some input quantum state rho. We're also given some output observable O. And the goal is to be able to predict a real value that corresponds to putting in the input state into some unknown quantum process. And after the evolution, measures these observable O. So we can see that this kind of function includes anything that's computable by a quantum computer. And in particular, if we don't place any constraint on the CPT map, this might even require exponential time quantum computation to compute such a function. And now let's look at some examples that fits into this framework. So one of the immediate application or immediate example of this framework is we would like to be able to predict outcomes of physical experiments. So for example, here, maybe the initial state is given by some classical input X that describes what's the initial configuration of the system. And this unknown CPT map corresponds to a physical process that happened in the experiment. And finally, the observable ode is something that the scientist measures. Another example corresponds to training quantum neural network. Here, we should think of the unknown CPT map E as being the quantum neural network that we would like to learn. So in the example 2, there will be often some structure in the CPT map. So it would just not be an arbitrary quantum process. And the observable O would correspond to a fixed observable that we know of and that we measure at the end of the neural network. Another example that people have looked at is in speeding up complex quantum dynamics. So here we should think of the unknown CPT map E that we would like to learn is the quantum evolution that we would like to speed up. So in this case, what we would like to do is we would like to train an ML model so that it can learn a more efficient way to do this prediction. So essentially a more efficient way to simulate quantum dynamics. In particular, the goal of the talk is the following. We're going to be given some n-qubit CPT map E that represents a potentially high complexity quantum process that might come from nature, or it might be a dynamic that we'd like to simulate, etc. What we're going to do is we're going to do some experiments, possibly very simple experiments, to create a data set about the quantum process, which can then be processed using a classical machine. So the classical machine does some learning. And after learning, it will create a learned model, which ideally would be of low complexity. And we can then utilize the low complexity learned model to make predictions about some other input states that we have not seen before and try to predict the property of the output state. So that's going to be the goal of today's talk. And I hope that's clear. And if there's any question, feel free to raise at any time. So the overview of the talk is the following. I'm going to start by looking at a classical version of the quantum problem. We're then going to look at a restricted version, and then we're going to generalize back to the original quantum problem that we set out to study. So let's begin by looking at the classical version of this quantum problem. So instead of having a high complexity quantum process, we can think of it as having a high complexity classical Boolean circuit that maps n bits to n bits. So instead of mapping n qubits to n qubits, it's now just bits. So the input here is now that n bit string x. And say we care about a very simple situation, which is we just wanted to predict the first output bit of the classical circuit. So in this case, we can write out the function as trace of z1. So the observable is z1. and the unknown process is C, which is a classical circuit, and the input is X. So we can first look at the worst case hardness of learning this function. And note that in general, this function is just an arbitrary exponentially long vector without any structure. And as a result, because if we don't place any constraint, this would just be a general function. And as a result, if we wanted to learn some model h of x such that for any input it's close to the output, we must query fc of x for all the input x, and that would result in a query complexity that grows exponentially. And the problem is not much easier if we consider the average case. Again, because the function is an exponentially long vector without any structure. So now if we wanted to learn a model h of x, such that when we randomly sample x, let's say from the uniform distribution over the Boolean hypercube, we want the average error to be, say, less than 0.5. It essentially means that we need to know what fc of x is for at least half of all x. And since there's, again, exponentially many different x, and the function has no structure, the query complexity would also be exponential. And furthermore, there's average case hardness that was known even for a shallow classical circuit. In particular, they showed that if one consider fc of x, so the circuit C, to be constant depths, say with majority gates, which is known as the classical TC0, then this remains like learning to an average error remains computationally hard for both classical and quantum computers. So there's a result from around 4 years ago that establishes this, essentially by reducing this problem to learning with error. So now we can see that the classical version of this quantum problem is very hard. And what we would like to do is to look at a restrictive version and somehow show that they're actually incomparable, and we can actually use that to design good learning algorithms. So now recall what the classical problem is. We have a high complexity classical circuit, and the input are just classical bits. And the goal is, say, to just predict the first qubit, Z1. And we see that this is hard. We can then look at a closely related quantum problem, where now the classical Boolean circuit is replaced by a quantum process. And the input, instead of being classical bit string, we consider a quantum product state. So now one question is, for this closely related problem, or one can think of it as a quantum version of the problem, is this harder than the classical problem? So one thing to know is that previously we talked about this function fc, which is essentially just a combination of this classical circuit here and Z1. We can equally define an observable O, which is just essentially performing a Heisenberg evolution of Z1 under this unknown quantum process. So in this case, the quantum problem is the same as there's an unknown observable O, and given some product state, we wanted to predict the expectation value of this unknown observable O. We're going to focus on a classical data set, which considers throwing in, say, random product state, and then we just measure the first qubit in the Z basis. So now this classical data set tells us about this unknown observable O that we would like to learn, because this essentially just contains a bunch of random product state mapping to a value YL, which is either 1 or -1, such that the expectation value of YL is equal to the true expectation value of the observable on the input state psi L. So now the task is the following. We are given this classical data set about the observable O, and the goal is that given a new state, which is, for simplicity, still a product state, how can we predict the expectation value of the observable accurately? So note how this connects back to the classical problem. In the classical problem, the observable O is essentially diagonal that correspond to this function fc. And all of these states, psi L, they're just bit strings. So in that case, it just exactly map back to the standard setting of pack learning a Boolean function. So this is essentially a quantum generalization to that, where we consider observable that have I of diagonal elements, and the input state can be a quantum, it's a quantum product state. So first of all, we can also look at the worst case hardness. And it's not hard to see that if we want to learn a model such that for all product state, the output is close, one could just think of the product state as being chosen to be the classical bit string. So now this problem exactly is at least as hard as the classical problem. So in that case, one can show that in a worst case situation, the query complexity is still exponentially high. However, as we have seen before in the classical problem, there's average case hardness as well. But now in this case, we're thinking of average case as we have some random product state, and we would like to predict it. And one could ask the question, is this problem still exponentially hard? And what's quite surprising is that while the classical version, where the input state is classical bit strings, the problem is exponentially hard. When the input states are random product state, surprisingly, the answer is no, and there exists an efficient learning algorithm that can achieve a good average case error in quasi-polynomial time. So that's essentially what I'm going to be talking about. So the key idea behind the learning algorithm is essentially a low-weight approximation. Or for people that are more familiar in the learning theory, classical learning theory community, it's also similar to low-degree approximation or low-degree function learning, etc. And basically the idea here is that suppose we write out the observable O in the Pauli basis as this form here. If we just truncate away all the high-weight Paulis and look at the low-weight approximation, essentially this O low here, there's a lemma which states that no matter what O is, as long as this has a bounded spectral norm, then we will have an average distance between O and O low that decays exponentially in K. We just need to take K to be some logarithmic number, and now we can guarantee that the average case distance is small. So another way to think about this is what it says is that for most product state, the expectation value on an arbitrary observable O will be close to the expectation value on the low degree approximation or the low weight approximation. And the strange thing here is that while the low weight approximation holds in the product state case, where we average over, say, tensor product of like hard random single qubit state, this low weight approximation doesn't hold in the classical version of the problem. So one way to think about that is the following, is that classical inputs, they're perfectly distinguishable from one another. Like every different bit strings correspond to orthogonal states, and they are essentially like boundaries or like these pointy edges on the entire thing. On the other hand, quantum inputs, when we have these random product state, they're not perfectly distinguishable from one another. And that makes them easier to essentially learn and predict. So now the basic idea is the following. We consider the original observable O, and we think of the corresponding low-weight truncation, the low-weight observable, and we just try to learn this low-weight observable O low by selecting some small k, and then just learning in the low-weight Fourier coefficient, or the low-weight Pauli coefficient, alpha p. In particular, there's a lemma which essentially tells us how one can estimate these alpha p. Basically, we just need to take the classical data set, take the corresponding value YL, and just kind of average over the entire data set with some normalization constant 3 to the weight of p. And on expectation, one can show that this exactly gives us the Pauli coefficient alpha p. So now the question is, well, this formula tells us how we can get alpha p on average. There will still be statistical fluctuation in these alpha p.
Robert,
and by taking
I'm sorry to interrupt. This is Marco speaking. Can you remind me where the quantum channel went, the E, like, because now you're just estimating O over the initial state, but the quantum channel disappeared.
Yeah, good question. So that goes back to here. So yes, there is a quantum process E that's here, but essentially we're considering a problem, yeah, where we just first do Heisenberg evolution on the output observable, and here we're focusing on the case when the output observable is just Z1. So that's O. So that it's got combined, and at the end, all we care about is learning O. Once you think of it as E is essentially secretly contained inside O. So now the question is, there will be statistical fluctuation if we don't take n to be very large, and how big we need n to be so that the statistical fluctuation will be small enough so that the learned O low will actually be close to the true low weight observable O low. In particular, what I'm going to show is that we only need to take the sample complexity to be extremely small. Just logarithmic in system size is sufficient to learn this low weight observable. In order to prove this fact, we need to go through a detour and talk about optimizing quantum Hamiltonian. So just kind of recap, what we've been looking at so far is we're trying to learn some unknown quantum process. Or more specifically, we wanted to learn the observable that corresponds to Heisenberg evolution of, say, Z1 under that unknown observable. And in order to understand that, somehow strangely, we need to go through a detour and talk about how one could optimize quantum Hamiltonians. So the task here is the following. We are given some n-qubit k-local Hamiltonian H, and we wanted to find a state psi that tried to maximizes or minimizes the expectation value or the energy. Particularly, we want to have a guarantee on the energy based on the description of the Hamiltonian, in particular based on these alpha p coefficient. And later it will become clear why that's important. So in particular, the proof of this, or the result that I'm going to talk about, will depend on a property that we called expansion property of the Hamiltonian. Basically, if we have a Hamiltonian that has an expansion coefficient of CE and a dimension of DE, what that terminology meant is that if we look at every size DE region, R, the number of Pauli coefficient, or the number of Pauli terms, such that the Pauli coefficient is non-zero, and that region dominates the Pauli term, or the region is fully contained inside the domain of the Pauli term, there's at most CE of them. So what these condition meant is the following. So suppose that we look at a size 2 region, R, correspond to these two qubits. So what are some examples of Pauli terms that will be counted? One example is this, which has only X on this qubit and identity here. Another one is, say, ZZ, because the domain exactly equal to R. Or another Pauli term, which is like Z, X, X, Y, Z, which fully covers the set R. That would also be counted. So yeah, so essentially these three Pauli terms all corresponds to the, would all be counted. And that would be going into this coefficient CE. So this might be a little bit technical, but let's look at a few examples to make it clearer. In particular, if we have a geometrically local Hamiltonian, then one can show that the dimension, this expansion dimension, is just equal to 1. Because for every qubit, it will only be covered by a constant number of Pauli terms in a geometrically local Hamiltonian. So in this case, the dimension will be 1, and the coefficient will just be a constant. On the other hand, if we have a general k-local Hamiltonian, where H is just the sum of general k-local Hamiltonian, then in this case, the dimension will become k, and the coefficient will grow exponentially in k. On the other hand, if we have, say, degree D two-body Hamiltonian, so what that meant in the literature is that we have a two-body Hamiltonian, and for every qubit, it's connected to at most D other qubits. So in this case, one could also show that the dimension is equal to 1, and the coefficient will grow linearly in a degree. I hope that kind of provides a better intuition for what this expansion property means. And a theorem that we established in the work essentially tells us how well we can find a product state approximation to say a high energy state or a low energy state. In particular, given the coefficient CE and DE and dimension DE, we can show that there's an algorithm that can find either a maximizing product state or a minimizing product state, such that if we compare the energy to a random state, there will be an advantage that's shown by this term here, which essentially depends on an R norm of alpha p. And there's some coefficient in front that's not particularly relevant. But essentially, this R norm is crucial. And this R norm depends, that this R corresponds to only the dimension. So if there's like a geometrically local Hamiltonian, then dE equal to 1. And if one plug it in, R would be equal to 1. On the other hand, if we have a more general K-log Hamiltonian, then dimension will be K. And when one plug it in, this R value will become closer and closer to 2. So note that 1 norm is much bigger than 2 norm. So if we have an advantage that's based on 1 norm, that means it's a larger advantage. But as K grows larger and the dimension grows larger, then it becomes closer and closer to 2, so the advantage will become smaller. So that's essentially an intuition of the following theorem, saying that essentially if you have a geometrically local Hamiltonian, then it's easier to optimize. But if you have a more general K-log Hamiltonian, then it's harder to optimize. In particular, this norm is characterizing this easiness and hardness. In particular, one can compare this result to several other results on optimizing Hamiltonians, and one can show that this provides improvement over existing results.
Can I ask a question about that?
Yeah.
So you say you have an algorithm that either finds a maximizing or a minimizing state. Does the algorithm also tell you whether it's maximizing or minimizing?
Yes.
Okay.
So it's based on a interesting technique that somehow it only optimizes one direction, and it's a priori unclear which direction it would optimize. And afterward, it will tell you. It will tell you that, oh, it's optimizing in the maximizing direction or the minimizing direction. Or sometimes it could optimize both. It can get different states, but both like making it larger and making it smaller energy. But yeah, but the guarantee only holds in one of it. So the algorithm roughly looks like the following. It basically just finds a product state that try to approximately optimize this psi edge psi. And the idea here is that we look at this Hamiltonian, and we just take a particular slice of it, which is each slice corresponds to, once you think of it as there's 1 body terms in Hamiltonian and 2 body terms and 3 body terms, each slice corresponds to a different number of bodies. So we take a slice that have the largest value of alpha p, essentially. And so now one can think of it as this Hamiltonian now only contains Pauli terms that have exactly weight k. And the algorithm looks like following. We essentially look at k replicas of the n-qubit system. For the first k-1 replicas, we're just going to select random product states. And then we're going to optimize the final replica. And then we're going to combine all these replica into an n-qubit state. And the way we do this is the following. We take the Hamiltonian edge. We use a method to lift this n-qubit Hamiltonian to an nk-qubit Hamiltonian using a technique in applied math called polarization. So we take the Hamiltonian edge, which acts originally on n-qubit. The polarization of edge is essentially given by just linearly extending polarization defined on Pauli operator. So we consider polarization of Pauli operator, and the polarization of the Hamiltonian is just a linear combination of them. And for each Pauli operator, the polarization is defined as follows. So say P is a three-body term that acts on the first three qubits, z, x, y, and then everything else is identity, then the polarization of P will correspond to a Pauli operator that acts on this n-qubit system, where it's just the average over things of all possible permutation. So like this term would be one of it, and there's also this, and this. There's a total of 6 of them, if k equal to 3. So that's kind of the intuition for the definition of the polarization. But one can write it down rigorously, but it's a little bit complicated. And now what we are going to do is we look at this polarized version of the Hamiltonian, which now is the Hamiltonian that acts on n-qubit system. And note that for the k-1 replicas, it would already been essentially randomly chosen. And then what we're going to do is we're going to optimize the third replica based on to maximize the energy of polarization of edge. And one can show that this can be done because of how polarization is being defined. So each Pauli term will only have one qubit acting on the final replica, and the previous ones would all be in previous replicas where the state has been randomly determined. So like things like this. As one can see, essentially it becomes an optimization problem that's purely qubit-wise. And hence one can solve efficiently and rigorously to find the optimum product state for maximizing polarization of edge. So now we do that, and perhaps we find these red vectors. And now what we're going to do is we're going to essentially utilize a weighted sum to combine all these different replicas to form a product state in each of them. So that's a kind of the intuition for an overview of the algorithm. And by carefully analyzing every step, one can essentially show that this theorem can be established. So that constitutes the first interlude on optimizing Hamiltonian. And then what I'm going to talk about next is how one can essentially use this quantum optimization algorithm and its corresponding rigorous guarantee to prove a generalized version of quantum Bohnenblust-Hille inequality. So this Bohnenblust-Hille inequality is an inequality that was known from 100 years ago in harmonic analysis. And very recently, people have found that using this Bohnenblust-Hille inequality, one can essentially use it to design very fast learning algorithm for learning low degree functions. And basically that's kind of how things are pieced together. So recall that we were starting out by trying to learn about quantum process, and by using Heisenberg evolution, we just need to learn observable. And one can essentially think of learning observable as learning the low degree approximation. So now we are essentially in the zone of trying to learn about low degree functions. And recently in classical learning theory literature, people have shown that this Bohnenblust-Hille inequality is very important for designing an efficient learning algorithm. So we need to prove a Bohnenblust-Hille inequality for the quantum case. And to prove that, we utilize this quantum optimization problem. So there's a long string of derivation. But now let's look at what this Bohnenblust-Hille inequality look like. Essentially, it says the following. We are given some observable O. Think of this observable O as the Hamiltonian that we're optimizing before. And say the observable has an expansion coefficient dE and dimension dE. Then we can show that there's going to be a norm constraint that's placed on these alpha p coefficient that is determined by the spectral norm of O. So for example, in our case, these observable will always have a spectral norm bounded by 1 because say we're measuring z1 at the end, which has eigenvalue 1 or n-1. So the spectral norm of O is just going to be 1. And this inequality essentially tells us that 1 is greater than or equal to some coefficients in front, and it bounds essentially the rth norm of these alpha Pauli coefficient. In particular, the R value will depend on the expansion dimension. The bigger the dimension is, the closer it will be into 2. But if the dimension is not very high, then it will be closer to 1. And in order to show this theorem, we essentially take the guarantee from the algorithm for optimizing quantum Hamiltonian, which essentially says that, oh, there's an algorithm that allow one to produce a product state such that the energy of the product state is better than essentially random state plus these Pauli coefficient terms. And one just need to note that the spectral norm upper bounds the energy. So then using the guarantee from the optimization algorithm, one can then lower bound this term by essentially this Pauli norm shown here. So that's kind of the rough idea for the proof of this theorem. So now again, to better understand what this theorem entails, let's look at some examples. So say the observable O is just a sum of geometrically local terms. Then in this case, the expansion coefficient is a constant and the dimension is just 1. So now by plugging into this theorem, what we see is that the 1 norm, that is just the sum of the absolute value for these alpha p coefficient, it will be upper bounded by the spectral norm of O. So this essentially tells us that if we have an observable that's sum of geometrically local terms, then there is a strong norm constraint on the Pauli coefficient, in a sense that either it's, so once you think of 1 norm as kind of a sparsity constraint, so either it's like very sparse and only hits on a few things, otherwise it's being very spread out in a strong manner. So that this essentially places a strong constraint on what kind of alpha p is possible. And there's other work on predicting ground state properties that essentially utilizes this inequality to obtain a fast learning algorithm. But what we actually need in this result here is when we consider observable O to be a sum of k local terms. So recall that going back much earlier to my talk, I have mentioned how if we're given some arbitrary observable, we can always do this low weight approximation. And all we need to focus on is to learn this low weight approximation. And note that this is an observable where it's it only has weights that it only contains essentially k local terms. So such an observable will be able to will satisfy essentially this this inequality that's shown here. What it says is that the spectral norm of O times some scaling that grows roughly exponentially in k, that object will upper bound the R norm of this alpha vector, where R is equal to 2k over k plus 1. So if k is just some small number, it would be somewhere between 1 and 2.
So is this tight?
Inequality,
Robert, is this tight?
Sorry?
Is this upper bound tight?
I think it's okay. So if one consider k to be constant, then yes, this upper bound is tight. But I think this term is not quite tight. This 2 to the order k log k is not quite tight. I think perhaps one can improve it to 2 to the square root k log k, something along that line. So this is a coefficient, and that can potentially be improved. But if one think of k as constant, then this is essentially tight. Yeah. And this is essentially the quantum analog of the Bohnenblust-Hille inequality. The Bohnenblust-Hille inequality considers essentially O to be diagonal, and one can think of that as like say a Boolean function, and it's a low degree Boolean function. And basically the left-hand side is just the Fourier coefficient that is often studied in Boolean functional analysis. the 2k over k plus 1 norm of the Fourier coefficient will be upper bounded by essentially the maximum value of the function. So if the function is bounded and is low degree, then suddenly there's a constraint on the Fourier coefficient that's much stronger than the typical setting. So the typical setting that one should have in mind is some kind of a 2 norm. It's very easy to prove a 2 norm bound. So like the Fourier coefficient's 2 norm will be upper bounded by, say, spectral norm. But here it's stating things that are stronger. It's stating that it's not just 2 norm that's bounded, but something smaller than 2 norm is bounded. And that essentially gives rise to like a approximate sparsity constraint on these Fourier coefficient. And that's why it enables efficient learning. So now that's back to the original talk on learning to predict arbitrary quantum processes. So recall again, the quantum problem is we have some highly complex quantum process that we would like to learn. And for simplicity, we're restricted to just looking at random product state input and measuring Z1 on the output. And now we can consider the Heisenberg evolution of the Z1 under this quantum process, which gives rise to this observable O. And what we're going to do is we're going to learn essentially a low-weight approximation to that observable O. That's defined by this O low. And there's a way to learn it based on this Fourier transformation lemma. And the key question that we set out to look at is how large should the data size n be so that the learned low-weight observable is close to the true low-weight observable. So now we have another insight that comes from this quantum Bohnenblust-Hille inequality, which states that the Pauli coefficient alpha is upper bounded by 2 to the order k log k times the spectral norm of O low. And essentially what this tells us is that the Pauli coefficient in this low-weight observable is approximately sparse because of the norm constraint. So think of it as like kind of like in one norm. If one have a one norm bound, then we can do compressed sensing style in order to reconstruct things very efficiently. But we don't just need one norm. If we get some kind of 1.6 norm bound, then we still get similar approximate sparsity that enables fast learning. And this is also an idea that was used in classical learning theory from 2022. Now the full ML algorithm in this case looks like the following. It's very, very simple. We just use the Fourier transformation lemma to get an estimate for these alpha p. And if we saw that the estimate is kind of small, like very close to 0, then we just set it to be exactly 0. And then then we just reconstruct the learned observable that way. So the reason that this algorithm works is because the Pauli coefficient is approximately sparse because of the norm constraint. So there's going to be many of them that are very close to 0. And the sparsity essentially tells us, like, if we just truncate them and set them exactly to 0, it doesn't really change the observable too much. But at the same time, because when we are using a very small n, there's going to be a lot of fluctuation in the estimate. And now if we just set it to 0, we just kill all these noise. So that helps a lot in reducing the sample complexity n. Now here's a guarantee. Essentially, for any small constant epsilon, given a training set size that grows logarithmic in system size, the prediction error will be upper bounded by epsilon times the spectral norm squared of the low-weight observable. And more precisely, one can also then combine. So note that here we're comparing just the learned low-weight observable and the true low-weight observable. And note that the true low-weight observable is close to the true observable O. So now by combining that, we have this theorem which says that for any small constant epsilon prime, given a training set size of order log n, the prediction error, which is the thing that we learned, and the true function based on this highly complex quantum process will be upper bounded by epsilon plus epsilon prime times the spectral norm squared of the low-weight observable. We can also put the epsilon and epsilon prime scaling into the sample complexity. Essentially, one would give rise to a quasi-polynomial scaling in terms of 1 over epsilon and 1 over epsilon prime. Essentially, the training set size has to scale logarithmically in n, and then roughly 2 to the order log 1 over epsilon, log 1 over epsilon prime. There's some log factor that was hiding in the total. So that's essentially a result that tells us that if we wanted to learn an arbitrary observable coming from Heisenberg evolved under this very complicated quantum process, we can always do so efficiently with a simple complexity that scales logarithmically in system size. So while the classical problem that we talked about is average case hard, it's exponentially hard, even in the average case, the corresponding quantum problem, where we replace the input from classical bit strings to random product state, actually becomes quasi-polynomially easy. Note that this also holds, like if you just consider an arbitrary classical circuit and put in random product state, then learning that would also be quasi-polynomially easy. But then the process can also be quantum. That's still the same.
Robert, can you have here some form of out-of-distribution generalization?
Yeah, that's a great question. I'm diving into that right now. Yeah. No, that's just a restricted version because we're looking at training from like random product state and then predicting on random product state. And what we're going to look at is what about predicting more general state, like some kind of highly entangled state. And that's essentially going back to our original quantum problem. So now the restricted problem looks like this: product state and then Z1. The more general problem, or original problem, is we wanted to be able to predict, say, some input state that are entangled, and then some more general observable. So now, instead of using the previous data set, what we're going to look at is this data set. Still going to feed in some random product state, but then in the measurement part, we're going to perform some randomized Pauli measurement. So every qubit measuring some random basis. So this can essentially be seen as the classical shadow of quantum processes. So the classical data set that comes out of it looks like the following. We have some random product state that was being chosen. And when we perform randomized Pauli measurement, we're also just going to collapse the whole state, which can be some highly entangled state, into a product state. Because when we measure in some bases, it would just collapse and it becomes product state. That's given by phi L. So both psi N and phi L, even though I wrote it in terms of like quantum state, they're actually classical. Like we know them classically. Because inputs, that's what we choose. And the output, that's the measurement outcome. So we know both of these objects classically. There's a classical data set written in a quantum language. So now we're given this classical data set, and we wanted to make prediction about, say, some highly entangled state, putting into the quantum process and measuring some more general observable. So what we're going to do is we're going to first consider transforming the classical data set for the particular observable that we care about. So note that the data set is there, and now the state rho comes in, and also the observable B comes in. We're going to take the observable B and then combine it with the classical data set to form a new classical data set that looks like this. So we're essentially just using the standard classical shadow formalism here. So we have some input state, and then instead of mapping to some output product state, we now map it to a real value YL that is computed by essentially this formula, which has the property that the expectation is the true one, and the variance is bounded by the shadow norm of the observable B. So one might ask, like, what's the shadow norm? And here one could again utilize this Bohnenblust-Hille inequality to study it. So let's say the observable B is some of, say, local terms, then geometrically local terms. Then the shadow norm can be shown to be upper bounded by the one norm of the Pauli coefficient. And then using the generalized Bohnenblust-Hille inequality, one can prove that the one norm is upper bounded by the spectral norm. So now this is essentially just order one, because we're focusing on observables that takes values between like -1 and 1. So now it's almost back to the original problem, because we now have this classical data set that have like some random product state and then a real number as an output. And where the real number, the expectation value of it is the same, is equal to this unknown observable O that corresponds to Heisenberg evolution of the observable B that we wanted to predict at the end. Now the only difference is the state part. So previously, we're just predicting some other random product state, but now what happens if we wanted to predict some more highly entangled state? Essentially, what we prove is that the lower approximation holds, not just for random product state, but for more general classes as well. In particular, we have the following lemma that says, if we have some arbitrary distribution D over any quantum state rho, as long as this distribution is essentially flat under single qubit rotation, what it means is, suppose there's some probability of sampling a state rho, then there will be an equal probability of sampling another state rho prime, where rho prime is equal to just like doing a single qubit rotation on rho. So for example, the rho here can be a random state that's the ground state or the thermal state of some generic geometrically local Hamiltonian. That would give rise to a distribution over quantum states that satisfy this flatness condition. In particular, under any of these distribution, we can show that low weight approximation is actually a good approximation and has an exponential decay in terms of k. Like the error decays exponentially in k. However, there's a slight difference. Like in the previous case, when we just don't do like out of distribution generalization, we just generalize to other random product state, then the scaling is better. It's 1/3 to the k. But now somehow when we're trying to prove things here, when we wanted to do some out of distribution generalization, then it still decays exponentially, but now it's 1/1.5 to the k. So now using this fact, we can go through the same line again. So O is close to O low, and we can just learn O low using random product state. And after learning O low, there's this lemma which guarantees that the learned O low will be close to the true observable O for these distribution, which can be over some highly entangled state. So now the full ML algorithm looks like the following. We're given this classical data set, product state to product state. We first take the observable, put it in, transform the data set. So now it's specifically for the observable O that corresponds to Heisenberg evolution of B under the unknown quantum process. Then we try to learn a low weight approximation of O. And the way to do that is we go through all the low weight Paulis, use the Fourier transformation lemma in order to estimate their coefficient, alpha p hat, and use essentially this Bohnenblust-Hille type argument that says alpha p vector is going to be quite sparse. So if we see like a value that's very small, we just truncate it, set it to 0. And then the learned observable is this O hat low. And then we just take O hat low, apply onto the input state rho, and one can utilize the same result and show that this will be approximately equal to trace of B apply onto E of rho. So now just to summarize some of the surprising aspect of this algorithm, is that first of all, we can learn to predict an n-qubit exponential size quantum circuit up to a constant relative error from only a logarithmic amount of samples, which seems kind of odd. And furthermore, this algorithm is computationally efficient. It's polynomial time for constant relative error and quasi-polynomial time for when we consider very small error. And furthermore, it has this out of distribution generalization aspect, which says that after learning from product state inputs, the algorithm can predict accurately also for entangled states, as long as it's kind of a spread out entangled state. And furthermore, this entire algorithm can be run on a classical computer. So to conclude, in this talk, in this work, we give a computationally efficient ML algorithm that can learn to predict output of a quantum process with arbitrary complexity. But note that this is a prediction in the average case. So it only predicts accurately when we have, say, random product state or some distribution that's flat under single qubit rotation. And in particular, this doesn't work when we consider just classical bit strings. Because of the average case hardness for random classical bit strings. Particularly, this result also highlights the potential that if we have some ML models, it can be used to predict outcomes of very complicated quantum dynamics, much faster than the process itself. Because no matter how complicated the quantum process is, no matter what the complexity is, it always has this low rank approximation underlying. So if we just learn that, then we will be able to predict accurately. And that's it for my talk. Thank you so much for listening.